How does it happen? Well, it happens in a very interesting way. So maybe I'll call it 7, Schrodinger equation. So as with any fundamental equation in physics, there's experimental evidence, and suddenly, however, you have to do a conceptual leap. You know, experimental evidence doesn't tell you the equation. It suggests the equation, and it tells you probably what you're doing is right. So what we're going to do now is collect some of the evidence we had and look at an equation and then just have a flash of inspiration, change something very little, and suddenly that's the Schrodinger equation. Alan told me that, in fact, students sometimes are disappointed that we don't derive the Schrodinger equation. Now let's derive it mathematically. But you also don't derive Newton's equations, F equal ma. You have an inspiration, you get it, Newton got it, and then you use it and you see it makes sense. It has to be a sensible equation, and you can test very quickly whether your equation is sensible. But you can't quite derive it. In 805, we come a little closer to deriving the Schrodinger equation, which we say unitary time evolution, something that I haven't explained what it is, implies the Schrodinger equation. And that's a mathematical fact, and you can begin unitary time evolution, define it, and you derive the Schrodinger equation. But that's just saying that you've substituted the Schrodinger equation by saying there is unitary time evolution. The Schrodinger equation really comes from something a little deeper than that. Experimentally, it comes from something else. So how does it come? Well, you've studied some of the history of this subject, and you've seen that Planck postulated quantized energies in multiples of h bar omega. And then came Einstein and said, look, in fact, the energy of a photon is h bar omega. And the momentum of the photon was h bar k. So all these people, starting with Planck and then Einstein, understood what the photon is. The quantum of photons, for photons, you have E is equal h bar omega, and the momentum is equal to h bar k. I write them as a vector because the momentum is a vector, but we also write them in this course P equal h bar k, assuming you move just in one direction. And that's the way it's been written. So this is the result of much work, beginning by Planck, Einstein, and Compton. As you may recall, Einstein said in 1905 that there seemed to be this quantum of light that carry energy h omega. Planck didn't quite like that. And people were not all that convinced. Experiments were done by Millikan in 1915, and people were still not quite convinced. And then came Compton and did Compton scattering, and then people said, yeah, these seem to be particles, no way out of that. And they satisfy such a relation. Now, there was something about this that was quite nice, that these photons are associated with waves, and that was not too surprising because people understood that electromagnetic waves are waves that correspond to photons. So you can also see that this says that EP is equal to h bar omega k as an equation between vectors. You see, the E is the first, and the P is the second equation. And this is actually a relativistic equation. It's a wonderful relativistic equation because energy and momentum form what is called in relativity a 4-vector. It's the 4-vector, this is a little aside on relativity, EP. 4-vector, the index mu runs from 0, 1, 2, 3. Just like the x mu's, which are t, and x run from x0, which is t, x1, which is x, x2, which is y, 3. These are 4 vectors, and this is a 4-vector, this is a 4-vector. This all seemed quite pretty, and this was associated to photons. But then came de Broglie, and de Broglie had a very daring idea that though this was written for photons, it was true for particles as well, for any particle. De Broglie says, good for particles, all particles. And these particles are really waves. So what did he write? He wrote psi of x and t is equal to a wave associated to a matter particle, and it would be an e to the I kx minus omega t. That's a wave, and you know that this wave has momentum p equal h bar k. If k is positive, look at this sign. If this sign is like that and k is positive, this is a wave that is moving to the right. So p being hk, if k is positive, p is positive, is moving to the right. This is a wave moving to the right, and has this momentum. So it should also have an energy. Compton said that this is relativistic because this all comes from photons. So if the momentum is given by that and the energy must also be given by a similar relation. In fact, he mostly said, look, you must have the energy being equal to h bar omega. The momentum, therefore, would be equal to h bar k. And I will sometimes erase these things. So what happens with this thing? Well, momentum equal to hk, we've already understood this as momentum operator being h bar over I d dx. So this fact that these two must go together and be true for particles was de Broglie's insight and the connection to relativity. Now, here we have this. So now we just have to try to figure out what could we do for the energy. Could we have an energy operator? What would the energy operator have to do? Well, if the energy operator is supposed to give us h bar omega, the only thing it can be is that the energy is I h bar d dt. Why? Because you go again at the wave function. And you take I h bar d dt, and what do you get? I h bar d dt on the wave function is equal to I h bar. You take the ddt, you get minus I omega times the whole wave function. So this is equal h bar omega times the wave function like that. So here it is. This is the operator that realizes the energy, just like this is the operator that realizes the momentum. You could say these are the main relations that we have. So if you have this wave function, it corresponds to a particle with momentum hk and energy h omega. So now we write this. So for this psi that we have here, h bar over I ddx of psi of x and t is equal to the value of the momentum times psi of x and t. That is something we've seen. But then there's a second one. For this psi, we also have that I, h bar ddt of psi of x and t is equal to the energy of that particle times x and t, because the energy of that particle is h bar omega. And look, this is familiar, and here the t plays no role, but here the t plays a role, and this is prescribing you how a wave function of energy E evolves in time. So you're almost there. You have something very deep in here. It's telling you if you know the wave function and it has energy E, this is how it looks later. You can take this derivative and solve this differential equation. Now, this differential equation is kind of trivial because E is a number here. But if you know that you have a particle with energy E, that's how it evolves in time. So came Schrodinger and looked at this equation, psi of x and t equal E psi of x and t. This is true for any particle that has energy E. How can I make out of this a full equation? Because maybe I don't know what is the energy E. The energy E might be anything in general. What can I do? Very simple. One single replacement on that equation. Done. It's over. That's the Schrodinger equation. It's the energy operator that we introduced before. Inspiration. Change E to E hat. This is the Schrodinger equation. Now, what has really happened here, this equation that was trivial for a wave function that represented a particle with energy E, if this is the energy operator, this is not so easy anymore. Because remember, the energy operator, for example, was p squared over 2m plus v of x. And this was minus h squared over 2m d second dx squared plus v of x, acting on wave functions. So now you got a really interesting equation, because you don't assume that the energy is a number because you don't know it. In general, if the particle is moving in a complicated potential, you don't know what are the possible energies. But this is symbolically what must be happening, because if this particle has a definite energy, then this energy operator gives you the energy acting on the function, and then you recover what you know is true for a particle of a given energy. So in general, the Schrodinger equation is a complicated equation. Let's write it now completely. So this is the Schrodinger equation. And if we write it completely, it will read I h bar d psi dt is equal to minus h bar squared over 2m d second dx squared of psi plus v of x times psi of x and t, psi of x and t. So it's an equation, a differential equation that is first order in time and second order in space. So let me say three things about this equation and finish. First, it requires complex numbers. If psi would be real, everything on the right-hand side would be real, but with an I, it would spoil it. So complex numbers have to be there. Second, it's a linear equation. It satisfies superposition. So if one wave function satisfies the Schrodinger equation, the sum of wave functions, and another wave function does, the sum does. Third, it's deterministic. If you know psi at x and time equals 0, you can calculate psi at any later time because this is a first order differential equation in time.